In Chapter 20, we're going to be looking at carbohydrates. These are the largest group of organic molecules in nature, and they make up actually 50% of Earth's biomass. Carbohydrates can be used to determine blood type, and it's also the backbone of our DNA. The definition of carbohydrates may be different to you in terms of what you've heard about in your diet, but in organic chemistry, a carbohydrate is a sugar or a starch. We can have polyhydroxyaldehydes, or they can be ketones. So polyhydroxy just means that there are multiple alcohols. And the definition of carbohydrate used to be that it was a hydrate of carbon. So you would have C, N, and then an H2O following that, and then N of that. Carbohydrates can come as monosaccharides, disaccharides, or polysaccharides. A monosaccharide is a simple sugar. That means that it can't be converted to any simpler compounds by hydrolysis. At the top of the sugars, we can have an aldehyde or a ketone. In honey, there is two common monosaccharides. One of them is glucose, which you can see the structure of here. At the top of glucose, this part right here, this one is a C double bond to an H, so this is an aldehyde. And fructose is made of a C double bond O with R groups on either side. This one is a ketone. So those are two main components of honey. A disaccharide has two linked monosaccharides. Usually it has at least one acetyl carbon. And if you remember the definition of that, that's one carbon that has two OR groups bonded to it. So one disaccharide is going to have at least one acetyl group, and these disaccharides can be hydrolyzed to monosaccharides. Lactose is a common disaccharide, and that is present in milk. We can see the acetyl carbon right here at the blue arrow. There's one carbon that has an O to an R group, so this would be the R, and it's bonded to another oxygen that has an R group there. So the rest of that molecule is R. In that disaccharide, there's an acetyl carbon. It's two individual sugars linked together, and those sugars happen to be in the cyclic form. A polysaccharide has three or more linked monosaccharides. There's usually at least one acetyl carbon, and these can also be hydrolyzed to monosaccharides. And examples of these include breads, starches, and pasta. The structure that we have here is one form of starch, which is a polysaccharide. All of the acetyl carbons are marked with the little asterisk here. And these can be hydrolyzed at each of those acetals to form smaller monosaccharide units. And the same thing can happen with the disaccharide that can be cleaved at the acetyl carbon. Carbohydrates are our storehouse of chemical energy. We can make carbohydrates from plants through photosynthesis. Glucose is a water-soluble compound and readily available in the bloodstream as a source of sugar. So energy can be stored in photosynthesis. Glucose is created from photosynthesis. We have 6 carbon dioxide molecules that react with 6 molecules of water. Once it reacts with sunlight and chlorophyll, that creates glucose and oxygen. And then energy from glucose is released in metabolism. A monosaccharide we discussed was one sugar or a simple sugar that can't be hydrolyzed. These can have 3 to 6 carbon atoms in a chain with a carbonyl, so that's C double bond O. They are characterized by the number of carbons in the chain. A triose is going to have 3 carbons. A tetrose has 4 carbons, pentose has 5, and a hexose has 6 carbons. And the ose ending tells us it's a sugar or monosaccharide. So this structure here is that of glyceraldehyde. It's the simplest sugar. It contains 3 carbons, and so this would be a triose. That's how we would classify that one. And if you wanted to get more specific about that, if we look at the functional group here, this is an aldehyde. So this one would be an aldotriose, or also an aldose. The aldose tells us there's an aldehyde. The aldotriose tells us we have an aldehyde on a 3-carbon sugar, and that carbon 1 is always going to be at the carbonyl. So this is 1, 2, and 3. So glyceraldehyde is an aldotriose. Dihydroxyacetone is a 3-carbon sugar, but our functional group here is a ketone, so this is going to be a ketose. Well, this one's also a triose. It's a ketose. So this would be a ketotriose. If we take a look at these two, they have the same chemical formula, but they're connected differently. These are constitutional isomers of each other. And then if we look at glucose here, this has 6 carbons. Our functional carbonyl group here is an aldehyde, which makes it an aldose. And then if we classify it more specifically, this will be an aldohexose. And then you could also call it a hexose. A hexose is just going to tell us it's a 6-carbon sugar. The aldohexose specifies that it's an aldehyde 6-carbon sugar as opposed to being a ketohexose. So if we look to classify each of these monosaccharides by their carbonyl group and the carbon chain, we're going to use the keto or aldo and then followed by the number of carbons in the sugar. So ribose has 5 carbons. This is a C double bond O to H, so this is an aldose. For 5 carbons, it will be an aldopentose. Fructose is 6. Our functional group here is a C double bond O, and there's carbons on either side of that. This is a ketose, so this will be a ketohexose. So a couple of practice problems for you here. Classify each of these monosaccharides by their carbonyl group and the number of carbons in the chain. So just like we did on the last slide, this is arabinose that we're looking at first. So you want to count up the number of carbons and then determine the functional group. I happen to have 5 carbons there, and this is an aldehyde. So this will be an aldopentose. Erythrulose has a C double bond O that's not at the top, so this is going to be a ketone. Or a keto. 4 carbons is tetrose. And then threose has 4 carbons. My functional group here is an aldehyde, so this will be an aldotetrose. All carbohydrates except dihydroxyacetone have 1 or more chiral centers. And remember, in order to have a chiral center, we need to have a tetrahedral carbon, and 4 different groups. Those are the requirements for a chiral center. So dihydroxyacetone is not going to have a chiral center because it has that ketone in the middle and it's symmetric. But every other carbohydrate will have 1 or more chiral centers. If we look at this one that is shown here, there's enantiomers of them drawn. The first one here is D-glyceraldehyde. And the chirality center is shown there. There's a hydrogen on that carbon, an aldehyde group, an alcohol, and then a C to an alcohol. The D-glyceraldehyde is the naturally occurring isomer where the OH is on the right. So D equals the OH on the right. The enantiomer of that is the L-glyceraldehyde. And L means that our OH is on the left. So this makes it L, this makes it D. When we draw Fisher projections, the horizontal lines come forward, which are the wedges. The vertical lines go back, which is a dash. So to draw D-glyceraldehyde in a Fisher projection, that's my backbone, and the OH is going to go on the right side here, and this hydrogen is going to go on the left side. So this is a Fisher projection. It kind of pushes everything flat down. The wedges in this 3D projection here are coming at you, and then the other groups are pointing away from you, but you kind of flatten everything out and draw it in the Fisher projection with the straight lines. Most monosaccharides will have more than one chirality center. Each of the carbons that are highlighted in blue there count as a chirality center. And even though it looks like all of them have the same things on them, their environments are different. That top blue carbon there has a hydrogen with an OH on the right side, an aldehyde above it, and then the rest of the chain below it. And that has a different environment than the second carbon that's highlighted there. That one has an OH on the left, a hydrogen on the right, and then molecule on top and molecule on the bottom that's different. So this structure here with the alcohol on the right, it's always the second to last alcohol or last chiral alcohol. The last one here, this is not chiral because there's two H's. If our OH here is on the right side, this is going to be D. So this is D-glucose. And then below we also have D-glucose because our OH here is on the right side. This is the naturally occurring enantiomer. So that last chiral OH there is on the right side, so that's going to tell us DRL. And then on the other version, this is the enantiomer. We can see our mirror plane there, and the OH on this one is on the left side. This is L-glucose. This one is not naturally occurring. So the location of the H and OH at every other chirality center is the enantiomer. So we can see each of those at carbons 1, 2, 3, 4, and 5 are mirroring the other molecule. Intravenous glucose can be given to patients, and it's also referred to as dextrose. This allows patients to have calories that they consume and also hydrates them, because if it's a 5% solution, only 5 grams out of 100 grams of that is going to be from the glucose. The rest of that is water. Let's look at this ribose here. This is an aldopentose, which means we have an aldehyde with 5 carbons. We're going to label all of the chirality centers. So to do that, we have to find tetrahedral carbon with 4 different groups. So I'll just label those with an asterisk. So this lower one here is not chiral because it has the same hydrogens. Both of the hydrogens are the same, so that's not chiral. This aldehyde is not chiral because it's trigonal planar. And each of these are chiral. So we have a carbon, there's a carbon with a bond to aldehyde, an H and an OH, so that one's chiral. The next one is also chiral. We have H2OH, the rest of the molecule. So there's no symmetry in these middle carbons, so those ones are all chiral. To classify whether or not the ribose is a D or an L, we're going to look at the last chiral carbon. Okay, so the OH is on the right, it's D. If OH is left, it's L. Our last chiral carbon is not number 5, it's actually going to be number 4. Because 5 we said was not chiral. And this alcohol is on the right side, so this one is D. And now to draw the enantiomer, I'm just going to draw the mirror image. I'll start with the original. So there's the original. You can draw your aldehyde this way. and then my OHs should face each other. So it's kind of like you just flipped it like a pancake over when you do the drawing. The most common monosaccharide is glucose, which is present as sugar in our blood sugar measurements. Glucose is the most abundant sugar. It is the building block for starch and cellulose. It gets transported in our bloodstream to provide energy for cells upon metabolization. So once our body breaks down the carbohydrates into glucose, we can use that for energy. A normal blood sugar range is around 70 to 110 milligrams per deciliter. And any excess sugar is going to be converted to glycogen or fat, which is a polysaccharide. Insulin is made in our pancreas. It regulates blood glucose, it stimulates uptake of glucose in tissues, and then converts it to glycogen. Diabetics do not have enough insulin, and they have to maintain their insulin levels with injections or other medications. So there's a picture here of a patient that is using insulin injections in order to maintain proper blood glucose levels. Another common monosaccharide is galactose. It's one of the sugars that makes up lactose. The other sugar that makes up lactose is the stereoisomer of glucose. So between glucose and galactose, they only have one chirality center that is different. So if we compare the first aldehyde, that's the same. On the second one, the OHs are on the right side. On the third carbon, they're on the left side. But in the middle, those mirror each other, and then the rest of it is the same. So these would be diastereomers, if you remember that term. And if you recall, the diastereomer has at least two chiral centers, which we have here, and they're not enantiomers of each other. A lot of the chiral centers match up. One of them is different, so that's going to make this pair a diastereomer. If you have galactosemia, this is an inherited disease that's rare. People that have this disease cannot metabolize galactose, so they must avoid cow's milk and other milk products. If they do consume milk products, the galactose can accumulate and cause cataracts, cirrhosis, and even intellectual disabilities. Galactosemia is not the same as being lactose intolerant. Another common monosaccharide is fructose, or fruit sugar. It's one of the monosaccharides in sucrose, which is table sugar. And this is also a ketohexose that we saw is present in honey. It is twice as sweet as table sugar. And the natural form of this is D-fructose. Our last chiral carbon here has an OH on the right side, which makes it a D. And then our carbonyl here is a ketone. So that's our ketohexose. Some products that are labeled as light have fewer calories because they use half as much fructose as sucrose for the same level of sweetness. A couple of slides ago, we saw that there were some cyclic forms of sugars, and we can now learn how to draw them. In order to do that, we have to give ourselves a refresher on how to draw acetals. If you remember back to our ketone and aldehyde chapter, we have an aldehyde plus an alcohol, and we're going to draw a hemiacetal. So I start with my carbon skeleton. We chop off one of these guys or split it. So I have an O here, and then my OR from the alcohol is going to add, and the hydrogen goes over here. So this is my hemiacetal. If we had a compound in nature that had an alcohol plus the carbonyl aldehyde, that is not stable. So what can happen is, instead of having an alcohol that's external, this alcohol reacts internal. So I can kind of redraw this so that they're in the same neighborhood. So this is carbon 1, 2, 3. So there's my alcohol that's really close. The alcohol on carbon 5 can wrap around and react with a carbonyl. and those will form the hemiacetal. This is the O from the aldehyde. There's an H. That's carbon 1. So this is 2, 3, 4, 5. And then here's my alcohol from before. I'm going to form a new bond here. So this would be the R prime, and then this gets protonated to make the OH. So here is my hemiacetal carbon. When we draw these hemiacetals, that OH can do an attack from the top or the bottom. So I'm just going to redraw this a little bit differently without the aldehyde hydrogen there. So we can see the OH is close by. And if we think about that aldehyde being flat, that OH can come in from the top and attack, or it can come in from the bottom and attack. So because we can have a bottom and a top attack, we can have two possible different what they call anomers. So I'll draw both of those and then I'll tell you about them. If the alcohol attacks from the bottom, we're going to get the alpha anomer, where the OH is on the bottom. So this right here is called an anomeric carbon. This one is also the anomeric carbon. And an anomeric carbon is just a fancy way of saying that it's the hemiacetal carbon. So the alpha anomer means that our OH is pointing down, and we can remember that because the alpha looks like a fish that is swimming down below. And the other one is the beta anomer. The beta looks like a butterfly that's flying above. So the alpha anomer has the OH down below on that anomeric carbon or the hemiacetal carbon, and the beta anomer has the butterfly flying up above or the OH flying above on that anomeric carbon.